Hello, it's me. I'm back and I'm online and you're at home and no one can interrupt me. So we are going to continue with where we left off when I last saw you. We have been looking at endothermic, exothermic reactions. We have been looking at the energy level diagrams in those things. So I'm not going to go over those again now. I'm going to carry on with where we were up to and then pushing on to do some new stuff so we can keep up with our learning. So we're going to start here by looking at something called a reversible reaction. Now, I have done this with you so far in the past. In a standard reaction, you have the two reactants here, chemicals, I've called them A and B, and those are the things that react together, and then they produce products. In this case, I've called the products C and D. So these are the things that go in, and these are the things that are made in a reaction. But in a reversible reaction, the products, the reactants turn into the products, and then when you turn your back, the products come undone again and turn back into the reactants, and then the reactants go back into the products, and the reaction's going backwards and forwards all the time, which is why we call it a reversible reaction. It's not a one-way street, things go backwards and forwards. And I used an analogy of these two people here. There's person X and person Y. They both have a shovel, they're both on either side of a wall, and their job is throw the sand over the wall. Now at the start of the reaction here, person X has got all of the sand. So they are going to be very successful in throwing the sand over the wall. Person Y is not going to be so successful at the start because the sand that lands is going to be spread all over the place. Going to have to scrape it into piles. And this person will be throwing some of it back over the wall, but there's going to be a lot more coming that way because this person has got a big pile of sand here. Now, as time goes on, this person's pile of sand will reduce, and this person's pile of sand will increase. And then once you get to the point where the two piles of sand are the same height, assuming that these are identical people with identical shovels, then we have got what we call a point of equilibrium, where the sand going from left to right is going over at the same rate as the sand going from right to left. And so the forward reaction and the backward reaction are happening at the same rate, and this is called a point of dynamic equilibrium. Now, if we were to give this person here some more muscles, for example, and maybe a bigger shovel, they now have an advantage over this person here. So this person will be much more efficient at throwing sand over the wall. And so their pile would end up much smaller, and this person's pile would end up much bigger. You will never get to the point where this person's got rid of all of their sand, because once they're down to a very small pile, it doesn't go over quite so quickly. So you still have got an equilibrium point, and that pile of sand will stay roughly the same size, and that pile of sand will stay roughly the same size. And by changing the conditions of an experiment, you can change this equilibrium point. We started off with a 50-50 equilibrium, and now we've got something like an 80%, 20% equilibrium. And this is using an analogy of people throwing sand over a wall, but it is just by giving one side of the equation an advantage over the other side that you can move this equilibrium point so you have more of the products or more of the reactants. And the things that we can do, we can put energy in to make these reactions go at a different rate and change the point of equilibrium. So we could increase the temperature, we could increase the concentration, just have the reactants or the products are squeezed in a little bit tighter, and so that so there's more of them in there to react. And we could increase the pressure, so again squashing them into a smaller space. Right, so that is dynamic equilibrium. That you have a reversible reaction, it goes both ways, but if you change the conditions, you can make this equilibrium point move further one way or another. So the advantage on this side is with person X because they've got more of an advantage, but it doesn't push everything across. You've still got some stuff coming back, but if you keep coming back and taking a picture every 10 minutes, it's going to look pretty much the same because they've reached this point of equilibrium. And you can change that by changing the temperature, the concentration and the pressure of various things. Right, now are we ready for some higher tier stuff? Because this is talking about someone called Le Chatelier, who came up with a principle, and he was saying that if you increase the temperature If it is an endothermic reaction, a reaction that you have to put energy in to make it happen, then if you increase the temperature, you'll make that endothermic reaction happen quicker, and so you will favour that side of the equation. You'll adjust your equilibrium point accordingly. Another one, which is the one that you just have to think about ever so slightly, is about changing the pressure. Now, if you're changing the pressure and a gas is turning into another gas, as we got over here, then we need to have a little bit of a think about this. Now, this one is the one that's in the book. It's called NO2, so that's a nitrous oxide, and I've drawn the nitrogens as a black atom here, and the oxygens, the two oxygens, as two white atoms here. And it says for every two of these, two lots of NO2, you get one lot of this larger molecule, which has got two nitrogens and four oxygens. So you can see this is what you start off with. So if I had 6 of these things here, you end up with 3 of these things here. So looking at this, you can see there is a greater pressure on the left-hand side than there is on the right-hand side. And if I was to squeeze in a few more NO2s in here, all of a sudden it would put a lot more pressure for them to turn into these things here. So if you increase the pressure on the side where there isn't very much, where there is lots of gas already, it's going to speed up that reaction. It's going to push the equilibrium point across, because this side of the reaction is going to be going faster than the other side. But because this is a reversible reaction, and some of these are coming undone again and turning back into these, what if I was to increase the pressure on this side and throw some more of these in? This actually wouldn't help the reaction at all, because they're trying to force more of them across here, but it's already quite tightly packed in here. So if you are increasing the pressure, it favours the side which has got less pressure in there. So that is the Le Chatelet's principle. But it's all talking about changing the temperature, changing the concentration, and changing the pressure. Now, as with all of these things, I'm basing them on your AQA GCSE chemistry book, which you have access to on the Caboodle website. And we have been looking at topics C8.8 and C8.9. Okay, so that's it. Yeah, well, I think I've covered that. So there will be more to come, but do some of the questions in the books and watch out for more videos. Thank you very much.